Hi all, it's Saturday and hope you guys are enjoying your Saturday night. And we are in this second video of NumPy lecture. So this is the part two of the NumPy videos, and then we are moving forward with wherever we stopped, and then we would cover the other topics in this video. So to let's not waste much of our time and directly start into this video. So in the previous video, that is the part one of the NumPy, we covered the most important topic or the most important aspect of NumPy, that is why is NumPy faster as compared to pure Python lists. And we also made some code and we tried to compare the time taken to perform some operations, some mathematical operations, as well as how much bytes of memory does Python lists take and how much of does NumPy array takes. So we made these comparisons with the memory taken by lists and NumPy arrays, and then again the time taken to perform operations. So now let's move forward and see what is the next thing that we need to learn. So we covered this part. So first thing was about the memory thing, and then the second was about the speed, which is critical for AI, and the third thing is homogeneous data types. Now, what does this even mean? So when we speak about homogeneity, so something that has similar composition all over the thing that we are talking about, the homogeneousness about the thing of which we are talking about. So it should have same composition all over the place. That means homogeneity. And in these terms, or here, what it actually means, the homogeneity of the data type. So basically, if I have a list in Python, I can have different elements with different data types. So Python lists become heterogeneous. But when I say that I am declaring a NumPy array of data type int32, that means we are fixing the data type of each element to a int32 integer, or a 32 bits of integer, not bytes, bits of integer. Or int64 means 64 bits of integer, or int8 means 8 bits of integer. So that's how we are actually introducing the homogeneity in the NumPy array. So let's take an example and then understand it through that. So we are speaking about the homogeneity of NumPy arrays. The spelling might be wrong. Don't worry about that much. I don't think. Something that's more important is to understand what this concept is. So let's first declare a list in Python. So this is one, and then this is maybe hello, then this is true, and then this is 2.4 or 3.2, whatever you want to declare it as, 3.2, and then which data type do we have more? So even take, let's do something like this, maybe 1, comma 2, comma 3, comma 4. That's it. I think this much is enough. And let's loop in through this Python list. So let's do one thing that um, let's append the type of uh, each of the element dot underscore underscore name. So this is nothing but magic method of which we discussed in the previous lecture as well. For I in A. Okay. So after that, let's print this array. So you can call this as a type array is equal to this, and then print this type array. So print the type array. Let's print this much. So you can say this. This is a first of all a list, and or a Python pure list allows you to have heterogeneity into them. So here each of the element is of different data type, as you can see. So the first element, which is 1, is an integer. The second element, which is hello, is a string. The third element is true, which is boolean. Then float, which is 3.2, is a float. And then this is again in itself a list. So this is again one of the nicest part of Python, that we can have a list inside a list. So nested list is what it allows. So this is in case of pure Python lists. But if I write a NumPy array, so let me declare one of them, underscore homogeneous is something which would be np dot array. And then let's declare first of all something like this, and then after that immediately print something like this, the type of the array. This is uh, this array dot the data type function. So this is a inbuilt function in NumPy which gives you the data type of this. And for more clarity, can directly specify what is the data type of this. Let's make it first int 32. Okay, cool. And let's copy the same thing again and have this to be copied as well. Give me a second, it's not getting copied. Don't know. Think. Okay. Let's do something like this. Don't know why my keyboard is a bit malfunctioning. The control X thing. Okay, cool. And let's make this float 32, and let's change some of the numbers 1.1, 1.12, 2.0, 3.24, something 21, whatever you want to. Let's keep this 4 as it should. And let's make this as float, and let's run this cell now. Okay, so we can see the output as uh, mm, okay, I'm sorry, here it should be float. Okay, now it would give a correct answer. Yeah, so here we can see that it is showing this to be int 32 as the data type of this entire NumPy array. And what does this actually mean is that each of the element of this array would be a fixed 32 bits of integer. It would not allow, or for example, if I try to write something like this, if I do this thing, it's gonna throw error to me. So let's see what error is throw. What error does it throw? It shows a value error, and it shows that it is at this place. And what it gives is that invalid literal for int with base 10. So this is what it actually means, is that this is not something on which I can call this function int, because this is not an integer, that too with base 10. So that's the value error that it throws. And this it's homogeneous. It does not allows to have heterogeneity into it. I hope you guys get it. Just give me a minute. My keyboard is malfunctioning. I think it's out of battery. I would just bring my charger and then we can continue. Sorry for this, guys. Okay, let me plug in my charger. Okay, cool. Hope it works properly now. So yeah, that's what we were discussing. Here again we can write it. Homogeneity. Okay, cool. So I think you guys understood what is the basic thing or the basic concept here, that that pure Python list would allow you to have elements of different data types, but NumPy array does not allows it. So once you specify, or even if you don't specify, so maybe we can remove this part from here, also remove this part from here, and then run the cell. Still we get the same, we get the different answers, because here, but again try to understand that this is int, this is float. The only thing that I have changed is that it by default declares a 64 bits of integer, and here it declares a 64 bits of float. So here there's only change in the uh, what do we say, the bits it's taking to store one single integer, or the amount of maximum and minimum number of integers that it can allow. That's the only change. But ultimately this is an integer thing, and this is a float thing, so it can understand that this is completely integers and these are floats. So it would also allow you to have something with point and then again something extra added after the point. So this is the homogeneity in the NumPy arrays. So we can just comment it down properly, that um, NumPy arrays could not be heterogeneous because they allow only one specific data type for each of the element that is stored. Cool. So this is about the homogeneity of NumPy arrays. So that's what is being explained here, that Python lists allow mixed types. Mixed types means nothing but heterogeneous lists or heterogeneous things. So basically each element could have different data type. Flexible, but the CPU hates it because it again takes more CPU memory. So it also, like as we discussed, that in list each of the element is a Python object itself. So when we say Python object, it would have the all those four properties that we discussed in the last video. The only thing that would change is for integers, the last property is the integer value, but for float it would be something different, but for strings it would be something different. So that would change, but the other three properties would remain the same. So that's how it's going to work. And then NumPy enforces single data type, so it enforces, or rather it explicitly we are declaring that the data type should also be the same thing. Okay, even in this, the four properties that I said about, so the size field could also be a different thing, because the size field is for the integer. So how much big or small is integer, so size field could also be a different property depending upon whether it is there for the strings or not. But for integers it would be there, so size field would be there for the integers, but not sure whether it is going to be there for the strings or not. So that's how different Python objects would have different properties. So I think you got what does homogeneous data types mean. And now we come about the memory efficiency comparison. So here again, let's do one thing, the same thing that we did here. So first of all, let's copy this part. Mm, uh, okay. I don't know why my uh, keyboard is malfunctioning a bit. Not even a bit, it's malfunctioning a lot rather. Even after plugging in the charger. Okay, cool. Now it correctly. I think it might be because I got a software update, that too for Xcode specifically. So that might also be an issue. Let's not talk about this now. We'll talk about okay. Talk about it later on. But let's do one thing that first of all, let's have a list which would be equal to range of, again let's declare this n thing is equal to 1 million. Okay, and then a list of a range of numbers of n. So we have a list of a pure Python list with 1 million values inside it, and then a NumPy array, np underscore array underscore 1 would be equal to np dot arrange. Okay, the dot is not properly there. And then this you can declare this thing. But what we can do is we specify the data type. So let's specify the D type to be int 32 here. Sorry, np.int rather, np.int 32, and then copy the same thing. And let's keep this to be 8 bytes. Okay. Now what we need to do is we need to just do the memory comparison. So what we will do is let's see what we should be checking. So this thing remains the same. Total size here it would be actually the size of it, this is n, so we can directly multiply this with n, and then let's change new list with a list. And here also what we can do is we can, with either doing this thing, we can write it something like this, because we know that the first element is going to be 0. The size of the list in the in bytes would be this thing, and the size of all the elements in the list would be this thing. And now let's print the f and size of the NumPy array with each element of 32 bits would be equal to, you can write it directly, let's write it to be np underscore array underscore 1, and I just didn't change the name of this array, it should be 2. Okay, underscore 1 dot data type these many bytes, so we will divide this by 1e6. Now what, sorry, 1e6, 1e6, so these many MB. Okay, and then you can copy the same thing, and here you can just do it by 2. Okay, cool. Let's print this. Now here each element is of 8 bits. Okay, 8 bits, and just print this thing. What error did we got? NumPy unsupported operand divide by for what? Oh, I'm so sorry. This is not D type. This should be N bytes. I'm so sorry for using a wrong function. Okay, now it should work. Okay, cool. Uh, so what do we got? Size of each element. It's a bit malfunctioning. Let's run this thing again. The size of the list is this many bytes. Of course, it has to be, each element is 28 bytes. That's okay. Size of the entire list is this much. And then the total size, that also we can, mention over here, but I'm not sure why these two things are not getting printed. Let's print them in the below cell. Let's try. Okay. So we can see that, sorry for that. You can see that the NumPy array, which is 32 bits each element, has size of 4 MB. Okay, because of course it's taking more bits for single, uh, what do we say, for the single element. But here it's only taking 1 MB of data for storing 8 bits array for 8 bits of 8 bits of each element NumPy array. It's just taking 1 MB. So you can see even the comparison. And here one more thing that I forgot to add is you can print the size of size of the entire list, and all the elements should be this total size, these many bytes. We can convert this thing also in, I'm not sure why it's not printing anything after this. Let's print the same thing. Even, let's print that thing also. Yeah. Okay, so these mesh bytes, we can again divide this thing by 1 is 6, and that much MB is what we can write. MB. And we can do the same thing for this thing, this much MB, and then, oh no, size of the elements and the list. Size of the list. Oh, we need to do this for the size of the list. 1 MB, and here we can divide this size by 1 e to the power 6. 1 e to the power 6. So let's first do this. So see, the only size of the array or the list in Python, pure Python is 8 MB. Then the, let's print this cell again. Okay, the size of the entire list, that is this 1 MB plus 28 bytes into 1 million, that many number of bytes, divide by 1 e to the power 6, that many number of MBs, adds all to 36 point these many MBs. So if I minus 8 from this, it's approximately or even perfectly equal to how much, 6 and 2, so it's 18 MBs. So basically the size of each individual elements, that is 1 million elements of the pure Python list, sums up to 18 MBs of data. So 18 MBs plus 8.4 times 056 MB adds up to 36, not 18, sorry, 28 MB. What am I doing? This should be 28 MB. So 28 MB of data, it sums up to be 36.0000056 MB of data. So this is how it works. So you can again make the comparison. Here it's taking 36 MB of data, The same thing here with 32 bits each element, or 32 bits each integer element takes only 4 MB, and if I make it lesser, if I make the integer to be equal to 8 bits, it takes only 1 MB of data. So just try to understand how much is the difference between the memory that it consumes in terms of CPU, right? So this is the actual memory comparison, and that's what this memory efficiency comparison shows you. So you can see that it's approximately equal to a per list, per element it's 28 bytes, and total it's approximately 28 million. But here we got it to be, you know, 36 MB of it, and yeah, that's a perfect answer that we got. And 4 MB for 32 bits each element, that is 4 MB, and 8 bits for you know, sorry, 1 MB for 8 bits each element. So this shows how is the difference between the memory that it consumes, pure Python list and NumPy arrays with different bits of each element. So again here, then NumPy array is making it more memory efficient, you know, to perform various mathematical calculations. So if we are using a NumPy array, then we can make more calculations because it allows us to have more memory, as it takes lesser amount of memory as compared to the pure Python lists. Okay. Now this something that is the next topic is the mathematical power. So there are a lot of different things or different functions that NumPy has built in. So for example, if I again declare an array, maybe like 1 comma 2 comma 3 comma 4, okay, and let's try to print something like a into 2. So what we think, or what should be the expected behavior for each of us, is that it would actually try to multiply each element of this array with 2, but that is not something that happens. Rather, what it does, it repeats this entire array again. So it would be 1 2 3 4 1 2 3 4, and if I specify 3, it would what do we say, uh, repeat itself 3 times. So let's print this out. This is how it happens in Python lists. So if I specify this number to be 3, and again, this is what it happens. So this is the problem in pure Python lists. But if I again a underscore np, maybe numpy array np dot array, and let's it to be 1 2 3 4, and if I multiply this array with 2, so a underscore np into 2, it will give me it would multiply 2 with each element of the array, and then it would give me. So this behavior is called as vectorization in NumPy. So what does vectorization means is it allows you to perform different operations on the entire block or on the entire array at once. So here, for example, if I want to perform same thing in pure NumPy array, for example into this, what I have to do is for I in range of what, or for I in A, what I would do is I will multiply I with 2, and maybe I need to store this again into some different array. Let's call it A underscore mul underscore 2. Let's this be a empty array, and then append this integer into this array. Let's keep on appending it into this array. So dot append, and do this thing, and finally print this array or list. Let's run this. So we can see the output of this and this is same. But here what we are doing is we are looping through the entire list and then performing it element to element. Rather, herein it's performing vectorization. Basically, it multiplies each element of the array, NumPy array, by considering it as a vector, and it does that at once. So 1, 2, 3, 4, all of them would be multiplied by 2 all at once. Here we are performing element wise. So the time when I'm multiplying the first element or maybe 1 with 2 in pure Python list is different compared to when I'm multiplying it with 2. So when I'm multiplying 2 with 2, then 3 with 2 and 4 with 2. So these times are different because we at a particular point of given time we are just multiplying one single element. But in a NumPy array, all these 1, 2, 3, 4 all are multiplied with 2 at the same time. So it's not parallel processing, but rather it's a thing at the register level. We would understand about that a bit ahead. That we have where the registers are of 128 bits, then 256 bits, which allows you to store a lot of amount of integers at the same time and perform different mathematical operations on them at the same time. So this is the this is one of the thing that is allowed in NumPy array. And if I want to add, for example, 2 into this, so maybe I can write like this and print it. So it would directly add 2 to each of these elements. So 1 plus 2 is 3, 2 plus 2 is 4, 3 plus 2 is 5, and 4 plus 2 is 6. But if I want to again perform the addition, this multiply would be changed with plus, and if I print this thing, I would again get the same result, but then again here it's element wise, but when I'm doing this it's doing all at the same time. So this is one of the power of NumPy, where it allows vectorization, and this vectorization is nothing but it allows you to do different mathematical computations on a given array, NumPy array, all at once rather than doing it element wise. I hope you all get this thing. And also in NumPy you have directly direct functions. So maybe I want to do the square root of this NumPy array. So I would just pass in the array to this function np.sqrt, and I will get the square root of each element. So I got the square root of 1, the square root of 2, 3, 4, and yeah, that's it. So this is 2.0. We can try to print this thing so that maybe we can get a visually good answer. So yeah, it's again the same thing, but here it's more visible or more properly visible. So this is for 1 the square root is 1, for 2 the square root is this value, for 3 it is this, and for 4 it is 2.000. This is 1.000. So that's one function that you can use. The other function, that is np dot what do we say, exponential of this at exp, and then a underscore np. So what does this mean is this calculates the exponent of each of the element. So exponent is something that you guys can see what does exponent mean. So it what it does is e to the power 1, e to the power 2, e to the power, e is a constant value, and exponent means e powered by that value. So that's the exponent of that value. So if I want to say I want to calculate the exponent of 3, it means e to the power 3, and that e value is constant always. So that's the exponent. This is one thing. Now something that is even more interesting is let's try to do that. Uh, so first, let's try to declare the weights. So np dot random random numpy array of maybe size 4 comma 3, and uh, let's keep it like this only. So what we are doing here is we are declaring a numpy array of random numbers with shape 4 comma 3. So it's a 2D numpy array wherein it would have four, rows, four rows and three columns. And then I am declaring again an x which is equal to np dot one dimensional array, maybe 1 comma 2 comma 3 comma 4. So now here I am declaring sorry for the dollar sign, it should be this, declaring a one or 1D array, one dimensional array in NumPy. So there is something called as this is, so this you can consider as an input layer. So in training neural networks, you have an input layer, and then you need to initially multiply the input layer with weights which are randomly initialized. Try to understand. Yeah, these weights are randomly initialized, and when you train the model, these weights are, automatically optimized by the backpropagation algorithm to, fit in the perfect purpose of the training of that neural network. So these are randomly initialized weights of 4 comma 3 shape, and then this is a one dimensional array. So if you want to write shape of this, you write it something like this. So 4 comma 4 comma nothing. It's if it's 4 comma 1, it's a two-dimensional array, always remember. And let's try to do the matrix multiplication of this. So x at the rate w. So this at the rate is nothing but we are trying to multiply this x with w, and then print this A. So let's try to run this much first, and then we would see the other things. So we get something like this. Now, what is even this? So let's first of all do one thing. We would print individual of them. So W is a random thing, so we don't know what are the values of W. But in this case, X is fixed because it's an array, one dimensional array with elements 1, 2, 3, 4. But let's see what does W is. So this is W. It is a 4 cross 3 matrix. Now, if you guys want to see this thing, this is very interesting feature in NumPy, that this is a one dimensional array. What NumPy internally does is it converts it into a 1 comma 4 matrix. So it would convert it directly into a row vector. So this maybe I can write this thing in here. uh, X is initially a 1D array, but when we do this matrix multiplication, it converts the the 1D array to a 2D vector or a row vector of shape 1 comma 4. I think you get this. And the W matrix W matrix is of shape 4 comma 3. So basically we all know that if we want the matrix multiplication to be properly performed, or it should not give you an error or should not throw an error, then in order to make this happen, we should have the number of columns of this matrix, the first matrix, should the number of columns of this matrix should be equal to the number of rows of this matrix. So when I say that 1 comma 4, so you can consider it that this thing is converted to a row vector with one row and four columns. So here it's a one row and four columns. That is, first column is this, second is this, third is this, and fourth is this. And 4 comma 3. So this is already 1, 2, 3, 4 rows and 1, 2, 3 columns. So 1 comma 4 multiplied by 4 comma 3 should give you a vector, should give you a matrix of 1 comma 3. That is nothing but this matrix. So I think you guys get it. So what NumPy is internally doing is it converts this one-dimensional array into a two-dimensional vector of size 1 comma 4. But if I try to do this thing, if I try to, for example, do w at the rate x, it will throw an error. Now why is it throwing an error? Because w is 4 comma 3, and here if even if we converts into a column vector, of 4 rows and one column, still it's a mismatch of shapes. So 4 comma 3 and 4 comma 1, there's a mismatch of shapes, so it's not going to convert, or it's going to throw an error. So that is why this is throwing an error. And matrix multiplication input operand 1 has a mismatch in its core dimension 0 with GU function signature. You just don't need to understand what all this is. Size 4 is different from 3. It's so basically it's showing the same thing, that size 4 means the 4 cross 1 vector is different than 4 cross 3 matrix. So 3 and 4 here are different, so it should be same. If those are same, then only we can perform the matrix multiplication. I think you guys get these things. And after this, we can print other things as well. So we can print the print something like the what we can say, data type of matrix A is A dot D type. Let me declare it as a F string. Similarly, we can copy this thing. Again, we can copy this thing, and we can write the shape of this matrix is A dot shape, and then the dimension of the matrix is ending, and then print. Let's print it. Okay, I'm so sorry. This should be x at the rate w. Now let's print it. Okay, cool. So we see that the data type of it is a float of 64. It's expected. The shape is 3 comma 1. Again, try to understand that this is not a 2D array. Okay, this is a 1D array with just 3 elements. So if I include this into some other multiplication, then it would internally try to convert it into a two-dimensional vector with either a row vector or a column vector, depending upon how it is trying to match the dimensions of the multiplication that we are trying to complete. And the dimension of this A matrix is 1, of course, because that's what I said, it should be a 1D array. So I hope you guys get this, because this is very important thing. As in, you will see this x at the rate w and w at the rate x a lot when we try to do the first forward pass to a neural network. So these are things which would be used in training the neural network. So try to get hold on what we are trying to say here. So this is the mathematical computation power that NumPy offers. So you can see that it's so amazing that it directly converts this into a 2D vector and also understands that whether it should be a row vector or a column vector. So that's the mathematical computing power or ability that NumPy provides. The same thing is explained over here as well. I will share you once this is done. Now, something that is even more awesome in NumPy is broadcasting, the concept of broadcasting. So we have also previously seen this thing. So let's copy the same thing. Maybe this thing. Let's copy this. So here, what actually we have is we have an array, a NumPy array like 1, 2, 3, and 4, and we are trying to multiply it with 2, right? With the scalar 2. So uh, let's not take multiplication, let's take addition. Multiplication would make it a bit more uh, complex. So, or it would change the definition of it mathematically. Rather, let's take addition. So now we know that we can perform matrix addition. Consider this thing as a matrix, because if we want to perform addition, let's try to assume, or let's assume that this is getting converted into a 2D matrix, or a 2D row vector, which is nothing but one row and four columns, then we know that if I want to perform addition on this, it should be a 2D vector with same dimension. So what Python or NumPy does internally is it converts this two into something like this. So 2 comma 2 comma 2. Are you getting it? So here we are trying to broadcast these two across the columns. I hope uh, get this concept. And then it would try to add this two. So this is one of the thing. If I want to give you a more better example into 3D, so you can see that it's doing the same operation. Let's do it on you know uh, two-dimensional array. So for example, I have np.array, and I have something like 1 comma 2 comma 3, and then I'm sorry for that, let's do it 4 comma 5 comma 6, then comma, and 7 comma 8 comma 9. Okay, so this is, let's assume that this is my NumPy array, and I am you know trying to make another NumPy array. Let's keep it to be bias, or VAS equals to, let's make it np.array, and let's keep it a one-dimensional array. So let's keep 1 comma 2 comma 3. Okay, now what and let's add this to and first see the answer that we get, or even do we even get an answer or not. Name bias, oh, I'm sorry, BIAS. I declared it. Okay. So we got an answer. And if you see what is happening is this 123 is added to this 123 and we get 246. Then this 123 is added to this 456 and we get 579. Right? Then this 789 is added to 5812. So what NumPy internally does it converts this 123 into something like this. So 1 comma 2 comma 3 comma, let's copy the same thing, and then again copy the same thing. So if you see here, it's actually increasing the dimension of this 123 from a one-dimensional array to a two-dimensional array and broadcasting this 123 across the column. So across the column we are increasing the or we are adding that 123 123. Are you getting this thing? So we are adding extra rows but across the columns. Okay, and here here we added extra columns, 2 to 2. Are you getting this thing? So that's the concept of broadcasting. So basically it broadcasts 1 2 3 across columns or rows, and this is nothing but broadcasting in NumPy. So in order to perform any mathematical operations, this is the thing that we have. Okay, and that's what is being explained over here itself. So that you have a scalar broadcast. So if I have 1 2 3 as an array and then add 10 to it, it would be like 10 10 10. Similarly, I want to multiply it, same thing would happen. And then I have a 2D array and I add a bias to it, then it broadcasts it something like this. Okay. Now the next concept is of multi-dimensional array support. So we can have numbers of different dimensions in we can have NumPy arrays of different dimensions inside NumPy. So let's do one thing. Let's take an example of the data set of which we would have a NumPy array of which and the same data set that we would use to train our neural networks. Here the values would not be exact, but try to understand with the dimensional point of view and the shape point of view. So let's make that array. So let's call this as grayscale. Grayscale. Let's go images and np dot random dot uh, random array of shape 32 comma 28 comma 28 comma 1. So now try to understand what we are doing. So these are nothing but 32 images of dimension 28 comma 28 comma 28 cross 28. Okay, so basically how this would look is for example, I start my array over here, then I would have 32 things inside this array first of all. Okay, so maybe so how I can write this rather than doing it in this way, let's do it something like this. Okay, and so on 32 times. So we would have such 32 arrays inside the initial array. Then inside each of these 32 we would have arrays like this. Let's do dot 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 28 times. Then inside each of these we would again have arrays which would be 28, so not 38, sorry, 28 times. So we would again have 28 times such arrays, and each of these would have some value inside it, that is 1. So 28 cross 28 and 32 such matrices of images is what we are declaring here. So if you want to see, we can directly print this grayscale images thing. Let's print. Okay, so you can see here. So see, you see this one of this 32. So you would have like this 32, and inside this you would have 28. Inside that you would have 28. Inside that each of them you would have 1. So that's how this thing is being getting declared, or you can see it over here. So you would at this level you would have at this first level you would have 32. This level you will have 28. At this level you would have 28. So basically this you would have 28 such values, and each of these 28 would have some one value inside it. That's what this thing means. and let's try to print different properties of this NumPy array. So let's print the shape of this array. We can write shape of this NumPy array is uh, we always forget the have string to write, should be np dot, sorry, not np, what, grayscale, yeah, grayscale images dot shape. Okay, then uh, let's copy this thing. Dimensions some array should be ending. Then what else do we have? Shape dimensions, data type. This some array is d type. And then let's do one more thing, that memory consumed. Memory consumed by this array is this much n bytes, and then let's divide it by 1 e to the power 6, this much amount of MBs. Let's print all this data. And so see, the shape of this NumPy array is it's 32 comma 28 comma 28 comma 1. Dimension is 4 dimension. Now see, the most amazing part, or the most amazing thing about mathematics or algebra is, specifically algebra, is that you don't have to imagine everything that you are actually doing. So here the dimensions are 4, and visually we could not think of dimensions more than 3, but algebraically we can play with any number of dimensions. So because we know what are the basic set of rules that we need to apply, so what we do, we first apply them on 2 or 3 dimensions, and we know that these set of rules work on 2 and 3 dimensions, and we try to scale them up on increasing the number of dimensions. So here the number of dimension is 4. In actual, deep learning training and neural networks training, we would have arrays of 100 dimensions, 1,000 dimensions, where we just don't want to imagine them. But NumPy would be able to, do the calculations easily on them at a very faster rate as compared to, basic lists in Python. Again, we saw what are the reasons. So the data type is again float 64, and it's taking almost about 0.200784 MBs of data. So this is, this is multi-dimensionality. So basically it supports NumPy arrays of various dimensions. This is a very important property or feature of NumPy, that it has multi-dimensionality, because most probably in most of the times we need to play with a lot of higher dimensions in NumPy, in artificial intelligence or in training neural networks. So that's why this multi-dimensional support is extremely important. You know. So this thing again, so this is an MNIST data set that we would explain this, in further concepts. So I think this much is again enough for today's video, because I think these concepts are again some higher concepts which I would personally try to do in some other video. But I hope today's video was more of understanding NumPy as compared to just understanding its internals. And I hope you guys are enjoying my videos, and keep supporting, and try to please follow, like, subscribe, comment on these YouTube videos. and let's learn AI together and also understand it in very deep sense rather than just superficial understanding it. Thank you guys. Thank you for the video. Thank you for your time. Bye.